Hello, and welcome to Time Lore. Tonight, we begin a journey far beyond memory, far beyond history, and even beyond time itself. This is not a story of events or of moments that happen one after another. It is a story about what existed before, after was possible. Take a slow breath. There is nowhere you need to go, nothing you need to understand right away. Just allow the story to unfold gently, one idea at a time. And so we return to where we began, but with deeper understanding. In a place where time did not exist, in a moment before space was born, in that infinite darkness where even nothingness had no meaning. What was there before the story of our universe began? We have explored quantum foam and false vacuums, eternal inflation and cyclic bounces, holographic projections, and mathematical existence. We have contemplated nothing, probed the nature of time, questioned the meaning of existence itself. And what have we learned? That the question is deeper than we imagined. That multiple answers might be partially correct. That the boundary between physics and metaphysics is blurred at the very edge of existence. That wonder and mystery persist despite scientific progress. The universe revealed by modern physics is stranger than ancient myths imagined, yet also more comprehensible. We cannot see beyond the Big Bang directly, but we can theorize, calculate, constrain possibilities through observation. Perhaps future discoveries will answer definitively what existed before. Perhaps not. But the question itself, the act of asking, theorizing, wondering, reveals something essential about consciousness and its place in the cosmos. We are the universe asking where it came from. We are matter contemplating its own origins. We are temporary patterns seeking eternal truths. This paradox, this strange loop of existence questioning existence, may be as close as we come to ultimate meaning. As you drift into sleep, as consciousness fades into the mystery of dreams, remember, you are made of star stuff, shaped by cosmic evolution, carrying within you the same creative fire that ignited the Big Bang itself, whatever came before it. The question remains eternal. The mystery persists. And in that mystery, in that eternal questioning, we find our deepest connection to the cosmos. In a place where time did not exist, in a moment before space was born, in that infinite darkness where even nothingness had no meaning. What was there before the story of our universe began? This is a question that has haunted humanity since we first looked up at the stars. A question that challenges the very foundation of our understanding. Because to ask what came before requires time, and time, as we know it, did not exist. Tonight, we venture into the deepest mystery science has ever confronted. Not the Big Bang itself, but what may have existed in that timeless, spaceless realm before. Some call it the quantum foam. Others call it the eternal void. Scientists speak of false vacuums, bouncing universes, and infinite cycles. But perhaps the most profound realization is this. Our very language fails us here. Every word we use, before, after, existence, nothing, all of these assume time and space. And in the realm we're exploring tonight, neither existed. So let us begin, or perhaps, let us imagine what beginning means when there is no time for anything to begin in. Over the next hours, we will explore the theories, the mathematics, and the philosophical implications of what scientists believe may have existed in that timeless realm before our universe was born. Close your eyes, breathe slowly, and let us journey together to the edge of existence itself. To understand what might have existed before our universe, we must first understand what time truly is. This is not as simple as it sounds. Time feels like the most fundamental aspect of reality. We experience it flowing constantly, carrying us from past through present into future. But Einstein showed us something remarkable. Time is not an absolute river flowing independently through reality. Time is relative. It can stretch and compress. It can slow down near massive objects or at high speeds. Time is woven together with space itself, forming what we call spacetime. They are inseparable, two faces of the same cosmic fabric. You cannot have space without time, nor time without space. They are born together, exist together, and would end together. When our universe came into existence, space-time itself was born. The clock started ticking at that very first moment. There was no time before this, because time itself did not exist. This leads us to a profound paradox. If time began with the universe, then there was no time before the universe. And if there was no time, how can we speak of a before at all? This is not merely wordplay or philosophical musing. This is the edge of human comprehension, where our deepest intuitions about reality break down completely. Our brains evolved to navigate a world of cause and effect, of before and after. But at the boundary of existence itself, these concepts may simply not apply. The quantum vacuum. Imagine perfect emptiness, a void so complete that not a single particle exists within it. No light, no matter, no energy. Just pure, absolute nothingness. This is what most people envision when they think of empty space. But quantum mechanics tells us this vision is wrong. Completely wrong. There is no such thing as perfect emptiness in our universe. Even in the darkest, most remote regions of space, far from any star or galaxy, even in a laboratory chamber cooled to near absolute zero with all matter removed, something is always happening. The quantum vacuum is never truly empty. It seethes with activity. Virtual particles continuously pop in and out of existence, appearing for infinitesimally brief moments before vanishing again. An electron and positron materialize from nothing, exist for a fraction of a second, then annihilate each other and disappear. This is not theory or speculation. This is observed reality, confirmed by countless experiments. The Casimir effect, for instance, demonstrates that two metal plates placed very close together in a vacuum will experience a measurable force pushing them together, caused by virtual particles in the space around them. The quantum vacuum is not peaceful emptiness. It is a roiling ocean of potential energy, where the laws of physics allow brief violations of what we think of as the conservation of energy. Heisenberg's gift. This bizarre behavior of the quantum vacuum is permitted by one of the most fundamental principles in physics, Heisenberg's uncertainty principle. Werner Heisenberg discovered that at the quantum level, certain pairs of properties cannot both be known with perfect precision simultaneously. The most famous example is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving. But there's another pair of properties that obey this uncertainty principle: energy and time. The uncertainty principle tells us that for very brief periods of time, energy can fluctuate wildly. The shorter the time period, the larger the energy fluctuation that's allowed. A particle can borrow energy from nowhere, as long as it pays it back quickly enough. The universe keeps perfect accounts, but it allows very short-term loans. This means that even in a perfect vacuum, even in a state we might call nothing, quantum fluctuations are constantly occurring. Particles appear, borrow energy from the vacuum itself, exist briefly, then return that energy and disappear. The vacuum hums with this ceaseless activity. Now imagine applying this principle not to a vacuum within our universe, but to the state that existed before our universe. If quantum mechanics applies there, and we have every reason to believe it does, then that pre-universe state was not static nothingness. It was a quantum foam of possibility. Physicists call this pre-universe state the quantum foam. Picture, if you can, a realm where space and time themselves fluctuate. Not objects moving through space, but space itself appearing and disappearing, swelling and contracting at scales so small they defy imagination. At the Planck scale, about 10 to the minus 35 meters, space and time lose their smooth, continuous nature. They become grainy, foamy, uncertain. At this scale, the fabric of reality itself is subject to quantum fluctuations. Tiny bubbles of space-time pop into existence and vanish. Wormholes connecting different regions of this proto-reality open and close in instants. This is not empty nothingness. This is a state of maximum possibility, where every quantum state exists in superposition, where the distinction between something and nothing becomes meaningless. It is a state beyond our ability to visualize, because visualization requires space and time. And at this level, space and time are not yet stable realities. Some physicists propose that this quantum foam is eternal, existing in a timeless state. Others suggest it had its own beginning, though what that could mean is unclear. What they agree on is this. From this seething quantum foam, under the right conditions, a universe can emerge. Not through any external cause, not through any divine intervention, but through the simple application of quantum mechanical laws to the fabric of reality itself. One of the most remarkable phenomena in quantum mechanics is tunneling. In our everyday world, if you roll a ball toward a hill and the ball doesn't have enough energy to reach the top, it simply rolls back down. It cannot pass through the hill or tunnel through it. The barrier is absolute. But in the quantum world, particles can do exactly that. An electron facing an energy barrier it shouldn't be able to cross can sometimes appear on the other side. It tunnels through the barrier, not by going over it or around it, but by exploiting the quantum uncertainty that governs reality at the smallest scales. The probability of tunneling depends on the height and width of the barrier and the properties of the particle. For everyday objects, this probability is so vanishingly small that we never observe it. But for quantum particles, it happens constantly. Now apply this concept to the universe itself. In the quantum foam state, reality exists in a kind of energy well. It takes energy to create space and time, to bring a universe into being. There is a barrier, an energy requirement that must be met. But quantum tunneling provides a way around this barrier. The proto-universe can tunnel from the quantum foam state into a state where space-time exists. It borrows the necessary energy from quantum uncertainty, and once space-time is created, that energy becomes real, woven into the fabric of space itself. This leads us to one of the most profound and controversial ideas in modern physics. The universe may have emerged from nothing through a purely quantum mechanical process. No cause, no creator, simply a quantum fluctuation in the void. The physicist Alexander Vilenkin proposed what he calls the quantum tunneling hypothesis. In this model, the universe begins in a state of literally nothing. No space, no time, no matter, no energy. Just the laws of quantum mechanics themselves, existing as mathematical possibilities. From this state, quantum tunneling allows a tiny bubble of spacetime to appear. This bubble is unimaginably small, far smaller than a proton, but it contains within it all the energy that will eventually become our universe. And crucially, it begins to inflate. This is not an explosion into existing space. There is no existing space. The bubble creates space as it grows. Time begins to tick as the bubble expands. Reality itself comes into being, not from any external cause, but from the inherent instability of absolute nothingness under quantum mechanical laws. To our minds, this seems impossible. How can the laws of physics exist before the universe? How can nothing give rise to something? But these questions assume a temporal framework, a before and after, that doesn't apply to this process. The laws of quantum mechanics are not objects that exist in time. They are timeless mathematical truths. But there is another vision of what existed before our universe, one that doesn't require something to emerge from absolute nothing. Instead, it proposes that something already existed, a false vacuum state. To understand a false vacuum, imagine again a ball on a hill. But this time, the hill has a complex shape. Near the top, there's a small valley, a depression where the ball can rest. It appears stable there, sitting quietly. But this is not true stability. This is not the lowest energy state the ball can occupy. Lower down the hill, there's a deeper valley, the true minimum. If the ball could reach that valley, it would settle there permanently. But there's a barrier between the small upper valley and the deep lower valley. The ball would need energy to climb over that barrier, and it doesn't have that energy. So it sits in the false vacuum, the upper valley, in a metastable state. It could remain there forever, in principle, but in practice, quantum mechanics provides a way out. The ball can quantum tunnel through the barrier, suddenly appearing in the true vacuum below, releasing enormous energy in the process. This false vacuum model suggests that before our universe, there existed a quantum field in just such a metastable state. It was stable enough to persist, perhaps for a timeless eternity, but it was pregnant with potential energy, waiting for the quantum fluctuation that would trigger its decay. When a false vacuum decays, the process is violent and sudden. At some random point in the false vacuum, a quantum fluctuation occurs. A small region tunnels from the false vacuum state into the true vacuum state. This creates a bubble. The walls of this bubble represent the boundary between the false vacuum outside and the true vacuum inside. And these walls move. They expand outward at very nearly the speed of light, converting more and more of the false vacuum into true vacuum as they grow. The energy difference between the false vacuum and true vacuum, the energy that was locked up in the metastable state, is released. This energy is enormous, far more than enough to create all the matter and radiation in our observable universe. But here's the crucial point. This energy doesn't explode into existing space. The bubble itself creates space as it expands. Inside the bubble, space-time comes into being. The laws of physics, as we know them, activate. Particles can form, forces can act, matter can clump together under gravity. Outside the bubble, in the false vacuum, time may not exist in any meaningful sense. or it may exist in a different form, governed by different laws. We cannot know because we are inside the bubble. Our entire reality, everything we can observe or measure or even conceive of, exists within this bubble of true vacuum that formed when the false vacuum decayed. The specific quantum field that is proposed to exist in this false vacuum state is called the inflating field. This is not a familiar field like the electromagnetic field or gravitational field. It's a hypothetical scalar field, meaning it has a value at every point in space but no direction. In the false vacuum state, the inflating field sits at a high energy value, like our ball in the upper valley. This energy is potential energy, stored in the field itself, not manifested as particles or radiation. The false vacuum appears empty, but it contains this tremendous potential. When the inflating field begins to decay, rolling down from the false vacuum toward the true vacuum, it releases this potential energy. But it doesn't release it all at once. The field rolls slowly at first, and as it rolls, it drives inflation, a period of exponentially rapid expansion of space itself. During inflation, space expands faster than the speed of light. This doesn't violate relativity, because nothing is moving through space faster than light. Space itself is expanding, carrying everything in it along for the ride. In a tiny fraction of a second, a region smaller than a proton can expand to many times the size of our observable universe today. As the inflating field continues to roll toward the true vacuum, it eventually reaches the bottom. When it does, it oscillates, and these oscillations decay into particles. The potential energy stored in the field converts into kinetic energy, matter, and radiation. The universe heats up, fills with particles, and begins the hot, dense phase we call the Big Bang. But here's where the story becomes even more extraordinary. The false vacuum doesn't decay everywhere at once. It decays in bubbles at random points due to random quantum fluctuations. Each bubble becomes a universe, expanding rapidly inside, but isolated from all the other bubbles. And while these bubbles are forming and expanding, the false vacuum between them is also expanding. In fact, the false vacuum inflates faster than the bubbles within it grow. This means that even though universes are constantly being created, the amount of false vacuum never decreases. It actually increases. This is the theory of eternal inflation, proposed by physicist Alan Guth and developed further by Andrei Linde, Alexander Vilenkin, and others. In this picture, inflation never truly ends globally, even though it ends within each individual bubble universe like ours. The false vacuum is eternal in both directions. It has no beginning, or if it does, that beginning is pushed infinitely far into the past by the eternal inflation process, and it has no end. New universes bubble off continuously, forever, but the false vacuum remains, always inflating, always creating new space where more bubbles can form. Our entire observable universe, spanning 93 billion light years, containing hundreds of billions of galaxies, is just one bubble in an infinite foam. And each bubble may have different properties, different laws of physics, different values for fundamental constants. This eternal inflation scenario leads inevitably to a multiverse. Not a multiverse of parallel timelines or alternate histories, but a multiverse of disconnected regions of space-time, each with potentially different physical laws. The laws of physics as we know them may not be fundamental. They may be accidents, properties of how the inflaton field decayed in our particular bubble. In another bubble, the electron might have a different mass. The speed of light might be different. Gravity might be stronger or weaker. There might be more dimensions of space, or fewer. Some bubbles might have laws of physics that don't allow atoms to form. Others might allow atoms, but not stars. Others might be so dominated by dark energy that structures never form at all. Our bubble happens to have laws that allow complexity, stars, planets, chemistry, life, consciousness. This raises the anthropic question. Why do we find ourselves in a universe with laws that permit our existence? The eternal inflation answer is simple. There are infinitely many universes with all possible laws. We necessarily find ourselves in one of the rare universes where observers can exist, because we couldn't exist in the others. This is not a satisfying answer to everyone. Some physicists find it too convenient, too much like giving up on finding deeper explanations. But others argue it may simply be true. Reality may be far vaster and stranger than we ever imagined, and our universe may be just one tiny, comprehensible bubble in an incomprehensible infinity. If eternal inflation is correct, then the question, what existed before the Big Bang, has a clear answer. The false vacuum existed, eternally inflating, with no beginning. But this raises another question. What is the structure of this eternal inflaton? How do we think about something that has no beginning in time? One way to approach this is to think about the topology of spacetime itself. In our everyday experience, time is a line stretching from past to future. We're somewhere on that line, moving forward. But mathematically, time doesn't have to be a line. It could be a circle or a more complex structure. In eternal inflation, the global structure of time becomes ambiguous. Within each bubble universe, time has a clear direction and a clear starting point, the moment when that bubble formed. But the false vacuum outside the bubbles exists in a kind of timeless state, or perhaps a state where time is infinite in extent. Some physicists describe this using the concept of eternal time. The false vacuum has always existed and will always exist. The word always here doesn't mean for a long time, but truly eternal, with no beginning and no end. Individual bubble universes have beginnings, but the multiverse as a whole does not. Others prefer to think of it as timeless. The false vacuum exists outside of time, in a quantum state that doesn't evolve in the way we normally think of evolution. Time emerges only when bubbles form, only within the context of individual universes. But eternal inflation is not the only vision of what existed before our universe. There is another compelling possibility, one with ancient philosophical roots, but modern scientific formulation, the cyclic universe. Imagine that the Big Bang was not the beginning of everything, but rather a transition point. Before our expanding universe, there was a contracting universe. That universe grew old, its expansion slowed and reversed, and it began to collapse. Eventually, it contracted down to a point of extreme density and temperature. And then, instead of collapsing into a singularity, it bounced. This bounce is our Big Bang. The endpoint of one cosmic cycle became the starting point of another. The universe has been through this process before, perhaps infinitely many times. And it will go through it again. Our universe will expand, eventually reverse, contract, bounce, and expand again in a new cycle. This idea has appealed to thinkers for thousands of years. Ancient Hindu cosmology speaks of cycles of creation and destruction spanning vast eons. Modern physics gives this ancient intuition a mathematical framework. The cyclic model solves the problem of what came before the Big Bang with an elegant answer. Another universe came before. Not a different universe in a separate bubble, but the same universe in an earlier phase. Time extends infinitely into the past, through cycle after cycle. The key question for cyclic models is, what prevents the collapse from creating a singularity? In classical general relativity, a collapsing universe should form a black hole-like singularity where density and temperature become infinite and the laws of physics break down. But quantum mechanics may provide a way around this. At extremely high densities, quantum effects become important. The uncertainty principle prevents matter from being compressed into an infinitely small point. There's a minimum size below which quantum pressure pushes back against further collapse. This quantum pressure can cause a bounce. As the universe contracts to near the Planck scale, about 10 to the minus 35 meters, quantum gravitational effects become dominant. Instead of continuing to collapse, the universe reaches a minimum size and then begins to expand again. From the outside, if such a perspective were possible, this might look like a smooth transition. But from the inside, from the perspective of any observers in the universe, the bounce would appear as a Big Bang. The universe would seem to emerge from a hot, dense state and begin expanding. All evidence of the previous cycle would be erased by the extreme conditions at the bounce point. This is both elegant and troubling. Elegant because it eliminates the need for an absolute beginning. Troubling because it means we may never be able to detect evidence of previous cycles. The bounce might erase all information about what came before. The British physicist Roger Penrose, winner of the Nobel Prize for his work on black holes, has proposed a different kind of cyclic model. He calls it Conformal Cyclic Cosmology, or CCC. It's one of the most imaginative and mathematically sophisticated ideas about what existed before the Big Bang. Penrose's model doesn't involve a contracting phase or a bounce. Instead, it involves a radical reinterpretation of what happens in the far future of our universe. Current evidence suggests our universe will expand forever, accelerating due to dark energy. Eventually, in trillions upon trillions of years, all stars will burn out, all black holes will evaporate, and the universe will become cold, dark, and empty. In this far future, nothing remains but photons and other massless particles, spread across an ever-expanding space. Temperature approaches absolute zero. Time stretches toward infinity. But here's Penrose's insight. In this state, the concepts of distance and time become ambiguous. When nothing exists with mass, when there are no clocks to measure time, when space is infinitely expanded, how do you define what size means? Penrose proposes that this infinite future of our universe can be mathematically identified with the Big Bang of a new universe. The endless expansion and cooling becomes, in a sense, indistinguishable from a hot, dense beginning. The end of one aeon becomes the beginning of another, not through physical continuation, but through mathematical equivalence. The mathematical tool Penrose uses is called conformal geometry. In conformal geometry, you can rescale distances and times without changing certain fundamental relationships. Angles are preserved, causal structure is preserved, but absolute sizes can change. Think of it like zooming in or out on a photograph. The shapes of objects remain the same. Their relative positions stay constant, but their apparent size changes. Conformal transformations do something similar to spacetime itself. In the far future of our universe, when everything is spread out infinitely and time is stretched to infinity, Penrose applies a conformal transformation. He rescales spacetime in a way that compresses this infinite future into a finite region. And remarkably, when you do this, the geometry you get looks exactly like the Big Bang of a new universe. The smooth, cold, empty state at the end of one aeon maps onto the smooth, hot, dense state at the beginning of the next. They're not the same thing physically. One is genuinely cold and empty, the other is hot and dense. But mathematically, after the conformal transformation, they become equivalent. This is deeply strange and difficult to visualize. We're used to thinking of time as having absolute meaning, of size as being a definite property. But in Penrose's model, these become relative concepts, especially in states where there's nothing left to measure them against. What makes Penrose's CCC model particularly intriguing is that he claims it makes testable predictions. If our Big Bang was preceded by another aeon, and if that previous aeon contained massive black holes, then those black holes would have left imprints on our universe. When black holes evaporate through Hawking radiation over unimaginable spans of time, they release their energy in bursts. These bursts, occurring in the previous aeon, would create patterns in the fabric of spacetime that might persist through the conformal transition into our aeon. Penrose and his colleagues have searched for these patterns in the cosmic microwave background, the faint afterglow of the Big Bang that fills the sky. They claim to have found concentric circles of slightly higher temperature, exactly what black hole collisions in the previous aeon would produce. Other physicists are skeptical. The patterns Penrose identifies could be statistical flukes, random variations that happen to look like circles. The debate continues, with detailed analysis of the cosmic microwave background data from satellites like Planck and WMAP. But regardless of whether Penrose is right about the specific evidence, his model demonstrates something important. The idea of what came before the Big Bang is not pure speculation. It can lead to concrete, testable predictions. We may actually be able to glimpse the universe that existed before ours, encoded in subtle patterns in the oldest light we can observe. There is yet another approach to understanding what existed before the Big Bang, one that comes from a different attempt to unite quantum mechanics with gravity, loop quantum gravity. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes the behavior of particles and fields at the smallest scales. These two pillars of modern physics are incompatible in their current forms. When you try to apply quantum mechanics to gravity, the equations produce infinities and nonsensical results. String theory is one attempt to solve this problem. Loop quantum gravity is another. Instead of treating spacetime as a smooth continuum, loop quantum gravity proposes that spacetime itself is quantized, made up of discrete, indivisible units at the Planck scale. Space is not infinitely divisible. You cannot have half a Planck length any more than you can have half a photon. Space itself comes in minimum chunks, woven together into a network that physicists call a spin network or spin foam. When you apply loop quantum gravity to the very early universe, something remarkable happens. The singularity that appears in classical general relativity, the point of infinite density at the Big Bang, disappears. It's replaced by a bounce, similar to the one in other cyclic models, but arising from the quantum nature of spacetime itself. In loop quantum gravity, as the universe contracts toward what would classically be a singularity, quantum effects become strong. The fabric of spacetime resists being compressed beyond a certain density. A quantum gravitational repulsion pushes back against the collapse. The universe reaches a maximum density, still unimaginably high, but finite, and then bounces. The collapse becomes an expansion. What appears to us as the Big Bang is actually a big bounce, a transition from a contracting phase to an expanding phase. This means that before our expanding universe, there was a contracting universe, not necessarily identical to ours, but connected to ours through this quantum bridge at the bounce point. Time extends continuously through the bounce, though the extreme conditions would make any observation or measurement impossible at the bounce itself. Some information from the previous universe might survive the bounce. The quantum state of the universe, the distribution of matter and energy, could carry through in modified form. We might, in principle, detect traces of the pre-bounce universe in the patterns of our cosmic microwave background or in the distribution of galaxies. However, the extreme conditions at the bounce likely erase most information. It's like trying to read a book after it's been burned and the ashes stirred. Some statistical properties might remain, but detailed information is lost. The bounce acts as an information bottleneck, largely separating one cosmic cycle from the next. String theory offers yet another perspective on what might have existed before our universe. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. String theory requires extra dimensions beyond the 3 spatial dimensions we experience. Depending on the version of string theory, there may be 6 or 7 additional dimensions, curled up at scales too small to detect directly. The way these extra dimensions are curled up, their geometry and topology, determines the laws of physics in the remaining large dimensions. Different configurations give different particle masses, different force strengths, different fundamental constants. The number of possible configurations is enormous, perhaps 10 to the power of 500 or more. This vast collection of possibilities is called the string landscape. Each point in the landscape represents a different possible universe with different physical laws. String theory doesn't naturally select one point in this landscape. In principle, all of these possibilities could be realized. Combined with eternal inflation, this suggests a picture where different bubble universes explore different parts of the string landscape. Our universe occupies one point in this vast space of possibilities, but countless other universes occupy other points. What existed before our Big Bang, in this view, is the broader structure of string theory and eternal inflation, with bubble universes constantly forming throughout the landscape. String theory has also inspired another cyclic model, quite different from Penrose's. This is the Ekpyrotic universe, proposed by physicists including Paul Steinhardt and Neil Turok. The name comes from the ancient Greek concept of ekpyrosis, a cosmic conflagration that destroys and renews the world. In the Ekpyrotic model, our three-dimensional universe exists on a membrane, or brane, floating in a higher dimensional space. There's another brane parallel to ours, also floating in this higher dimensional space. These branes are slowly drifting toward each other, pulled together by forces in the extra dimensions. Eventually, the branes collide. This collision is violent, energetic, and appears to observers on either brane as a Big Bang. The energy of the collision heats both branes, fills them with matter and radiation, and sets them expanding apart again. But this collision is not a one-time event. The branes drift apart, slow down, and eventually begin approaching each other again. They collide once more, producing another Big Bang. The cycle repeats eternally. What existed before our Big Bang, in this model, was the previous cycle. Our brane was drifting through higher dimensional space, cool and empty after expanding from the previous collision. Then it collided with the other brane again, and our current universe was born. This model makes specific predictions about the pattern of temperature fluctuations in the cosmic microwave background, different from standard inflation. So far, observations seem to favor inflation, but the Ekpyrotic model remains a logical possibility. As we explore these various models of what existed before the Big Bang, we encounter another profound idea that may reshape our understanding of reality itself: the holographic principle. The holographic principle emerged from studying black holes. When something falls into a black hole, information about it seems to be lost forever. But quantum mechanics says information cannot be destroyed. This creates a paradox. Stephen Hawking and others realized that the information is not lost. It's encoded on the event horizon, the surface of the black hole. The three-dimensional information about what fell and gets encoded as a two-dimensional pattern on the horizon. The interior of the black hole is, in a sense, a holographic projection from its surface. But physicists Leonard Susskind, Gerard T. Hooft, and others realize this idea applies more broadly. Any region of space might be fully described by information encoded on its boundary. Our three-dimensional universe might be a holographic projection from a two-dimensional surface. If this is true, it radically changes how we think about the Big Bang and what came before. The question becomes, what existed on the boundary surface before our holographic universe was projected from it? Perhaps there was a different pattern on that boundary, corresponding to a different universe. Perhaps our Big Bang was a transition from one holographic pattern to another. This is highly speculative, but it shows how our understanding of space, time, and causation continues to evolve as we probe the ultimate questions. The holographic principle raises deep questions about the nature of information and reality. If our three-dimensional universe is actually encoded on a two-dimensional boundary, then what we perceive as solid matter, as space itself, as the passage of time, may all be emergent phenomena arising from more fundamental information patterns. This connects to what existed before the Big Bang in a surprising way. Perhaps the question is not what physical state existed before, but rather what information pattern existed before. The Big Bang might represent a dramatic reorganization of information on the holographic boundary, rather than the creation of spacetime from nothing. In this view, the universe is fundamentally made of information. Matter and energy are ways that information manifests. Spacetime itself is a canvas on which information patterns are painted. The laws of physics are rules for how information transforms and flows. Before our universe, there may have been a different information pattern, corresponding to a different physical reality, or perhaps no physical reality at all. The transition from that state to our universe would be an information processing event, a cosmic computation that rearranged the fundamental bits of reality. This may sound like science fiction, but it's grounded in serious physics. The discovery that black hole entropy, a measure of information content, is proportional to surface area rather than volume was one of the great surprises of theoretical physics. It suggests that information, not matter or energy, is the fundamental currency of reality. Recent work in theoretical physics has revealed an even deeper connection between information and spacetime. Quantum entanglement, the strange correlation between particles that can persist across any distance, may actually be what creates space itself. When particles become entangled, measuring one instantly affects the other, regardless of separation. Einstein called this spooky action at a distance. But physicists now realize that entanglement is not some mysterious force acting across space. Entanglement may be what generates the connectivity of space in the first place. This idea, explored by physicists like Juan Meldacena and Mark van Ramsdonk, suggests that space-time emerges from quantum entanglement. Regions of space that are connected because the quantum fields in those regions are entangled. If you could somehow remove all entanglement, space would fragment and cease to exist as a unified structure. This has profound implications for what existed before the Big Bang. If space-time emerges from entanglement, then before space-time existed, there was some kind of pre-entangled state. Perhaps a simpler quantum state with less structure, less connectivity. As entanglement patterns became more complex, space-time crystallized out of this quantum substrate, the Big Bang. Then, would not be an explosion in space, but an explosion of space itself, as entanglement patterns suddenly proliferated and created the connected, coherent space-time we inhabit. What existed before was a quantum state with different entanglement properties, perhaps simpler, perhaps just different in ways we cannot yet understand. As we contemplate these various theories about what existed before our universe, we must confront a question that some find uncomfortable. Why does our universe have the properties it has? Why do the laws of physics seem fine-tuned to allow the existence of stars, planets, chemistry, and life? The fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, the cosmological constant, appear to be precisely calibrated. Change any of them by even a small percentage, and the universe becomes inhospitable to life. Stars might not form, or they might burn out instantly. Atoms might not be stable. Chemistry might not be complex enough for biology. This observation leads to the Anthropic Principle. In its weak form, the Anthropic Principle simply notes that we should not be surprised to find ourselves in a universe compatible with our existence. We couldn't exist in a universe with different laws, so naturally we find ourselves in one of the rare universes where observers are possible. The strong Anthropic Principle goes further, suggesting that the universe must have properties that allow observers to exist. This raises questions about teleology and purpose that make many scientists uncomfortable. But if any of the multiverse theories are correct, eternal inflation, the string landscape, cyclic models with varying parameters, then the Anthropic Principle becomes simply a selection effect. There are countless universes with all possible laws. We find ourselves in one of the rare ones that permits our existence because we couldn't exist anywhere else. Some thinkers push the anthropic reasoning even further, suggesting that consciousness itself plays a fundamental role in the structure of reality. This is where physics meets philosophy meets metaphysics in ways that remain deeply controversial. In quantum mechanics, observation plays a special role. Before a measurement is made, A particle exists in a superposition of multiple states. The act of measurement collapses this superposition into a single definite state. But what counts as a measurement? What counts as an observation? Some interpretations of quantum mechanics suggest that consciousness is required to collapse the wave function, to make quantum possibilities into classical realities. Without observers, the universe would remain in a fuzzy superposition, never crystallizing into definite facts. If this is true, and most physicists are skeptical, then consciousness is not merely a byproduct of physical processes, but an essential ingredient in making reality definite. The universe needs observers, which means it needs laws of physics that permit observers to evolve. This would give a deeper meaning to the Anthropic Principle. The universe is not just compatible with consciousness, it requires consciousness to fully exist. What existed before the Big Bang, in this view, might have been a purely quantum realm of possibilities, waiting for the emergence of observers to collapse those possibilities into actualities. This is speculative and controversial, mixing physics with philosophy in ways that make many scientists uncomfortable. But it shows how the question of what existed before our universe connects to the deepest questions about the nature of mind and reality. The physicist Max Tegmark has proposed one of the most radical ideas about the nature of reality, the mathematical universe hypothesis. According to Tegmark, the physical universe is not just described by mathematics. It is mathematics. Physical existence and mathematical existence are the same thing. In this view, every mathematically consistent structure exists in the same sense that our universe exists. There is a mathematical structure that describes our universe, its particles, fields, forces, spacetime geometry. This structure exists as a mathematical object, and we are patterns within that mathematical object experiencing it from the inside. But our mathematical structure is not unique. There are infinitely many other mathematical structures, and all of them exist with equal reality. Some of them might be similar to ours, differing only in parameter values. Others might be radically different, with different numbers of dimensions, different types of particles, or laws that don't resemble ours at all. What existed before the Big Bang, in Tegmark's view, is not a temporal question at all. Mathematical structures do not exist in time. They are timeless, eternal in the Platonic sense. Our universe, as a mathematical structure, includes time as one of its dimensions. The Big Bang is simply the boundary of this mathematical object in the time direction. To ask what came before is like asking what comes before zero on a number line that starts at zero. The question misunderstands the nature of the structure. Time begins with our universe because time is part of our mathematical structure, not something external to it. Tegmark has classified different multiverse proposals into 4 levels, each more expansive than the last. Understanding these levels helps clarify what we mean when we ask what existed before the Big Bang. Level 1 is the simplest multiverse. If space is infinite and matter is distributed roughly uniformly, then every possible arrangement of matter must occur somewhere. Far beyond our observable universe, there are regions where events unfold exactly as they do here, simply because there are infinitely many chances for the same pattern to repeat. Level 2 is the multiverse of eternal inflation. Different bubble universes with genuinely different physical laws, formed from different decay patterns of the inflating field. This is where the fine-tuning of our universe gets explained as a selection effect. Level 3 is the many-worlds interpretation of quantum mechanics. Every time a quantum measurement occurs, the universe splits into multiple branches, one for each possible outcome. All possibilities are realized in different branches of the universal wave function. Level 4 is Tegmark's mathematical universe. All mathematically consistent structures exist. This includes all the lower levels, but goes far beyond them, encompassing structures that don't resemble physical universes at all by our standards. What existed before our Big Bang depends on which level you're considering. At level 1, our Big Bang is local, just one event in an infinite space. At level 2, it's the formation of our bubble. At level 3, it's part of the eternal evolution of the wave function. At level 4, it's a feature of our particular mathematical structure. Throughout all these theories, one concept remains stubbornly difficult to grasp: time itself. We experience time as a flow, a river carrying us from past through present into future. But physics tells us this experience is an illusion, or at least not fundamental. In Einstein's relativity, time is relative. Different observers moving at different speeds or in different gravitational fields experience time passing at different rates. There is no universal now, no absolute present moment that extends throughout the universe. Simultaneity is relative, observer-dependent. In quantum mechanics, time plays a special role, different from space. The equations of quantum mechanics require time to be a parameter, not an operator like position or momentum. This asymmetry between time and space in quantum mechanics is still not fully understood. When physicists try to quantize gravity, to create a theory of quantum gravity, time becomes even more problematic. In some approaches, like the Wheeler-DeWitt equation, time disappears entirely from the fundamental equations. The universe is described by a timeless quantum state. If time is not fundamental, if it emerges from something more basic, then asking what existed before the Big Bang may be asking the wrong question. Time itself came into being with our universe. There is no meaningful before, just as there is no meaningful north of the North Pole. The question contains a category error, applying temporal concepts to a realm where time does not exist. Yet we undeniably experience time. Events happen in sequence. Causes precede effects. We remember the past, but not the future. If time is not fundamental, how does this experience emerge? One possibility is that time emerges from thermodynamics. The second law of thermodynamics states that entropy, disorder, always increases. This gives a direction to time, an arrow pointing from ordered past toward disordered future. Perhaps our experience of time's flow is really our experience of entropy increase. In the early universe, just after the Big Bang, entropy was low. The universe was in a highly ordered state. As it expanded and evolved, entropy increased. Stars formed and burned out. Black holes formed and eventually will evaporate. The universe moves inexorably toward heat death, a state of maximum entropy where nothing can happen anymore. This entropy gradient, from low entropy past to high entropy future, might be what creates our sense of time's flow. Time is not a fundamental feature of the universe, but an emergent property of systems far from equilibrium, systems where entropy can increase. What existed before the Big Bang, in this view, might have been a state of even lower entropy. The cyclic models naturally incorporate this idea. Each cycle begins with low entropy and ends with high entropy. The bounce or transition to the next cycle somehow resets entropy to a low value, allowing time to flow again. But this raises a puzzle. Why was entropy low at the Big Bang? This is one of the deepest unsolved problems in cosmology. The puzzle of why entropy was low at the Big Bang is sometimes called the past hypothesis. It's a hypothesis because we simply assume it without knowing why it's true. The early universe was in a special, low-entropy state. But why? What mechanism or principle selected this particular initial condition? In ordinary physics, we don't need to assume special initial conditions. If you drop a ball, it falls due to gravity. The initial conditions, the ball's position and velocity, determine the details, but the general behavior is explained by the law of gravity. But with the second law of thermodynamics and the arrow of time, we seem to need a special initial condition. The universe began in a low-entropy state, and entropy has been increasing ever since. But the laws of physics themselves don't prefer low entropy to high entropy. In fact, high entropy states are vastly more probable. So why did the universe begin in an improbable state? Some physicists argue this is where we need to invoke the multiverse. If there are countless universes with different initial conditions, most will have high entropy throughout their history. Such universes would be featureless, with no arrow of time, no structure, no possibility of life. We find ourselves in one of the rare low-entropy universes because only such universes can contain observers. Others argue we need a new principle or law that explains why entropy was low at the beginning. Perhaps the bounce in cyclic models naturally produces low entropy. Perhaps the decay of the false vacuum creates a low-entropy state. The question remains open. Another approach to quantum gravity, called Causal Set Theory, offers a different perspective on time and what might have existed before the Big Bang. In Causal Set Theory, spacetime is fundamentally discrete, made up of point-like events connected by causal relationships. Imagine a set of points, each representing an event, something that happens at a particular place and time. Some of these points are causally related. One event can influence another. These causal relationships form a network, and the structure of this network determines the geometry of spacetime. In causal set theory, time emerges from the causal structure. The past consists of all events that can causally influence the present. The future consists of all events that the present can causally influence. Time's arrow comes from the direction of causality. This gives a new way to think about the Big Bang. Perhaps the causal set that represents our universe has a minimal element, an earliest event from which all other events descend. This would be the Big Bang, not an explosion in time, but the first element in the causal order. What existed before this first element? In causal set theory, the question has a clear answer: nothing. There are no earlier elements in the causal set. The Big Bang is not preceded by anything because precedence is defined by the causal structure, and the causal structure starts at the Big Bang. This doesn't mean the Big Bang came from nothing. It means the Big Bang is the boundary of the causal structure that constitutes our universe. To ask what caused the Big Bang is like asking what element of a set comes before the first element. It's a malformed question. We must consider one more possibility, one that moves from physics into metaphysics, the simulation hypothesis. What if our universe, including the Big Bang, is a simulation running on some substrate beyond our reality? This idea has been popularized by philosopher Nick Bostrom and others. If it's possible to create detailed simulations of universes, and if advanced civilizations create many such simulations, then statistically, we are more likely to be in a simulation than in base reality. The simulation hypothesis offers a straightforward answer to what existed before the Big Bang. The computational system running the simulation existed. Our Big Bang was the initialization of the simulation program. The laws of physics are the rules of the simulation. The fundamental constants are parameters set by the programmers. This might sound like science fiction, but it's philosophically coherent. And interestingly, it might be testable. If our universe is a simulation, there might be computational shortcuts, approximations that leave traces. We might find glitches, limitations in resolution, or other signs that our reality is rendered rather than fundamental. Most physicists don't take the simulation hypothesis seriously as a scientific proposal, but it serves a useful purpose. It reminds us that our intuitions about what's real and fundamental may be wrong. What seems like bedrock reality might be an emergent phenomenon arising from something deeper and stranger. Whether simulated or not, the question remains, what is the ultimate substrate? If our universe is a simulation, what runs the simulator? Does that substrate have a beginning? The question of origins simply moves to a different level. As we explore all these theories about what existed before the Big Bang, we must confront an uncomfortable possibility. We may never know the answer. Some questions may lie forever beyond the reach of science. Science works by observation and experiment. We form hypotheses, make predictions, test them against data. But the state before the Big Bang may be fundamentally unobservable. If the Big Bang erased all information about what came before, if the inflation period smoothed away all traces, then no amount of cleverness or technology will recover that information. This would not mean the question is meaningless. The pre-Big Bang state existed or didn't exist, regardless of our ability to know about it. But it would mean we're limited to mathematical consistency and theoretical elegance rather than empirical verification. Some physicists argue we should focus only on questions we can answer through observation. Others argue that even unanswerable questions can guide us toward better theories, can illuminate the structure of physics, can reveal deep patterns we might otherwise miss. The history of science offers hope. Questions that seemed unanswerable often become answerable as our tools and theories improve. Before telescopes, we couldn't observe the moons of Jupiter. Before particle accelerators, we couldn't probe the structure of atoms. Before gravitational wave detectors, we couldn't observe black hole collisions. Perhaps future technologies will let us peer back to the Big Bang itself, to read subtle patterns in the cosmic microwave background, to detect gravitational waves from the earliest moments, to test competing theories in ways we cannot yet imagine. There is something philosophically profound about conscious beings in the universe asking where the universe came from. We are arrangements of particles governed by physical laws, yet we can step back and question those very laws, that very structure. In quantum mechanics, the observer plays a special role. Measurements affect quantum states. The act of observation is part of the physics, not separate from it. Some interpretations go further, suggesting consciousness itself is necessary to collapse possibilities into actualities. If this is true, then the universe's history is not fully determined until it's observed. The quantum superposition of possible histories remains unrealized until observers emerge and, in some sense, select which history actually occurred. This leads to a strange loop. Observers exist because the universe had certain properties after the Big Bang. But those properties are only definite because observers exist to measure them. The universe is past and its present observers create each other in a kind of circular causality. Physicist John Wheeler called this the participatory universe. The universe brings observers into being, and observers bring the universe's history into being. Past and present co-create each other. If this view is correct, then asking what existed before observers is not just practically difficult, but conceptually confused. The definite classical past, including the Big Bang, emerges when observers make measurements. Before observers, there was only quantum superposition, unrealized possibility. This is one of the most mind-bending implications of quantum mechanics, and most physicists don't embrace it fully. But it shows how the question of cosmic origins connects to deep puzzles about the nature of reality and observation. Throughout this exploration, we've encountered multiple theories: eternal inflation, cyclic models, quantum bounces, string theory, loop quantum gravity, holographic principles. Each offers a different answer to what existed before the Big Bang. Are they competing theories or different aspects of a deeper truth? Many physicists hope for a final theory, a theory of everything that would unify quantum mechanics and general relativity, that would explain all forces and particles, that would account for the origin and structure of the universe. String theory and loop quantum gravity are attempts at such a theory, but neither is complete or confirmed. Perhaps these different models are like the parable of the blind men and the elephant. Each touches a different part and describes it accurately, but none sees the whole picture. Eternal inflation might be correct about the multiverse structure. Cyclic models might be correct about the bouncing mechanism. Holographic principles might be correct about the information structure. They could all be partial truths within a larger framework. Or perhaps the question of what existed before the Big Bang doesn't have a single answer because before isn't a well-defined concept at that boundary. Different mathematical frameworks extend beyond the Big Bang in different ways, and all are equally valid or invalid. The search for unity in physics continues. Each generation brings new tools, new mathematics, new perspectives. Questions that seemed impossibly difficult become tractable. The gap between what we know and what we can imagine narrows slowly but steadily. Beyond the physics, the question of what existed before the Big Bang touches on ancient philosophical questions. Why is there something rather than nothing? What is the nature of causation? Can anything be truly self-caused? Does existence require an explanation? Philosophers have grappled with these questions for millennia. The ancient Greeks debated whether the cosmos was eternal or had a beginning. Medieval philosophers argued about whether an infinite regress of causes was possible. Modern philosophers of science question whether the universe requires an explanation at all. Some argue that existence is brute fact, requiring no further explanation. The universe simply is, and asking why is a category error. Others argue that existence demands explanation, that there must be some necessary being or principle from which everything else derives. Physics brings new tools to these ancient debates, but doesn't necessarily resolve them. Science can tell us how the universe behaves, what laws govern it, how it evolved from early states to now. But whether it can tell us why there is a universe at all, why these laws rather than others, remains contested. The physicist Stephen Hawking famously asked, "What breathes fire into the equations? What makes a particular mathematical structure become actual, experienced reality rather than merely a logical possibility?" This question sits at the boundary between physics and metaphysics. Perhaps the question itself is confused. assuming a distinction between mathematical existence and physical existence that doesn't really hold. Or perhaps it points to something essential that physics alone cannot capture: the qualitative feel of existence, the why beneath the how. To understand what existed before the Big Bang, we must understand nothing. But what is nothing? This seemingly simple question reveals depths that challenge our deepest intuitions in everyday language. Nothing means the absence of things. An empty room contains nothing, but the room still contains space, air, quantum fields, virtual particles. It's not truly nothing. Remove the air. Now we have a vacuum. But even a perfect vacuum in our universe is not nothing. It contains quantum fields in their ground state. It contains the potential for virtual particles. It has energy, structure, properties. The quantum vacuum is not nothing. It's something quite specific. Remove space itself. Remove time. Remove all fields, all potential, all structure. What remains? This is what philosophers call absolute nothing. Not empty space, but the absence of space. Not the passage of time without events, but the absence of time itself. Not fields at zero energy, but no fields at all. Can such absolute nothing exist? Some philosophers argue it cannot. The concept is incoherent. Nothing cannot have properties, but we just described it, which means we gave it properties, which means it's not nothing. Others argue that absolute nothing is the default state. Something requires explanation, but nothing requires no explanation. Therefore, the deepest question is not what existed before the Big Bang, but why anything exists at all. Why is there something rather than nothing? Physics suggests that quantum mechanics makes absolute nothing unstable. Even nothing fluctuates, and these fluctuations can create something. But this assumes quantum mechanics applies to nothing, which is itself a profound assumption. Philosophers have long distinguished between contingent and necessary existence. Contingent things exist, but might not have. Their existence depends on something else. Necessary things must exist. Their non-existence is impossible or incoherent. Most objects in the universe are contingent. You exist because your parents existed, because Earth formed, because certain physical conditions were met. But could something exist necessarily, not depending on anything else? Some classical arguments for God rely on this concept. The universe is contingent, so it must depend on something necessary. This necessary being is what we call God. But this argument faces challenges. Why assume the chain of contingency must end? Why couldn't contingency go infinitely back? Modern physics offers a different perspective on necessary existence. The laws of physics might be necessary in a mathematical sense. If Tegmark is right, all mathematical structures exist necessarily. Our universe exists because its mathematical structure is consistent, and all consistent structures must exist. Or perhaps the quantum vacuum is necessary. Perhaps nothingness is unstable in a way that makes something inevitable. Perhaps existence itself is the default and requires no further explanation. These are not questions physics can answer definitively. They sit at the boundary where physics meets metaphysics. But they help clarify what we're asking when we ask what existed before the Big Bang. Are we asking about contingent precursors, or are we seeking something necessary from which everything else flows? The various cosmological models we've explored offer different answers. Eternal inflation makes our universe contingent on the false vacuum. Cyclic models make each cycle contingent on the previous. Mathematical universe hypothesis makes everything necessary through logical existence. One of the most difficult concepts to grasp is that time itself might have a beginning. We're so accustomed to time as the stage on which events unfold that imagining time itself coming into being seems impossible. St. Augustine grappled with this question in the 4th century. When asked what God was doing before creating the universe, he replied that there was no before. God created time along with the universe. Before time existed, there was no before. This answer seems like a dodge, but modern physics suggests Augustine was onto something. If time is part of space-time, and space-time began at the Big Bang, then time itself has no before. The question of what existed before time is like asking what's north of the North Pole. It applies a concept beyond its domain of applicability. But our minds rebel against this. Surely something must have existed before, even if that something was timeless. We struggle to conceptualize existence without temporal duration, being without becoming. Some models preserve temporal continuity by having time extend through the Big Bang into a prior phase. Cyclic models and bouncing models do this. In these frameworks, time is infinite in both directions, and the Big Bang is just a transition point, not an absolute beginning. Other models have time with a beginning but embedded in something larger. Eternal inflation, where our bubble has a beginning but the inflating false vacuum is eternal. Or mathematical universe, where our time is a dimension within a timeless mathematical structure. Which picture is correct? We may not be able to answer empirically, but the question illuminates how we think about existence, causation, and reality itself. There is something vertigo-inducing about contemplating these questions. What existed before the universe? Why does anything exist? What is the ultimate nature of reality? These questions touch something deep in human consciousness. We are finite beings asking about the infinite. Temporary patterns asking about eternity. Local observers trying to grasp totality. There's a poignancy in this. Conscious matter asking where consciousness and matter came from. For most of human history, these questions were the domain of religion and philosophy. Creation myths told stories of gods shaping chaos, cosmic eggs hatching, primordial waters dividing. These myths satisfied the deep human need to understand origins. Science has not eliminated this need. If anything, it has deepened the mystery while making it more precise. We know more about the universe than any previous generation, yet our knowledge reveals how much we don't know. The more we discover, the more questions emerge. The Big Bang is not the end of the mystery, but the beginning. Before the Big Bang there was what? A quantum foam? A false vacuum? A previous cycle? A mathematical structure? Nothing at all. Each answer raises new questions, opens new mysteries. Some find this frustrating. After all our progress, we still don't know the ultimate answers, but others find it exhilarating. The universe remains mysterious, reality deeper than our theories, existence itself an ongoing puzzle. We are privileged to live in an era when we can ask these questions precisely, when we have the mathematics and observations to constrain speculation, when the boundary between knowledge and mystery is clearer than ever before. Mystery is not the enemy of science. Mystery is what drives science forward. Every answer creates new questions. Every solved puzzle reveals deeper puzzles beneath. The question of what existed before the Big Bang may never be fully answered. Some aspects might be forever beyond observational reach. The extreme conditions, the erasure of information, the fundamental limits of what we can observe, all conspire to keep some secrets hidden. But this doesn't make the question worthless. The pursuit of understanding, even of the ultimately unknowable, shapes our theories, drives our experiments, expands our conceptual vocabulary. We develop new mathematics, new physical intuitions, new ways of thinking about existence. The history of physics is full of questions that seemed unanswerable becoming answerable. What are stars made of? How old is the universe? What happened in the first seconds after the Big Bang? Each of these seemed hopeless at one time. Each eventually yielded to human ingenuity. Perhaps future generations will look back at our uncertainty about what existed before the Big Bang the way we look back at 19th century uncertainty about atoms. Obvious in retrospect, but genuinely mysterious in its time. Or perhaps this particular question will remain forever at the horizon of knowledge, always approachable but never quite reachable. The ultimate origin, the deepest why, might be beyond any finite intelligence to fully grasp. Either way, the question enriches us. It reminds us that we are part of something vast, ancient, mysterious. We are the universe contemplating itself, asking where it came from, marveling at its own existence. We have journeyed through many possible answers to what existed before the Big Bang. Each offers insights. Each has strengths and weaknesses. Let us reflect on what we've learned. The quantum vacuum model suggests that nothing is never truly empty, that existence emerges inevitably from the quantum fluctuations inherent in physical law. The false vacuum and eternal inflation models propose an eternally inflating multiverse, giving birth to countless bubble universes, ours among them. The cyclic models, whether Penrose's conformal cyclic cosmology or the quantum bounce of loop quantum gravity, suggest our universe emerged from a previous phase, that the Big Bang was a transition rather than an absolute beginning. The Ekpyrotic model proposes colliding branes in higher dimensions. String theory and the holographic principle suggest reality is fundamentally informational, that our three-dimensional universe might be a holographic projection from a lower dimensional boundary. The mathematical universe hypothesis proposes that mathematical existence is physical existence, that all consistent structures are real. Each model makes different assumptions, requires different mathematics, predicts different observational signatures. Some might be tested with future technology. Others might remain forever theoretical. But underlying all these models is a common theme. The Big Bang was not the beginning of everything. Something existed before, whether we call it quantum foam, false vacuum, previous cycle, mathematical structure, or brane collision. Or perhaps the question itself is malformed, applying temporal concepts where they don't belong. What we've learned is that existence is stranger, deeper, more mysterious than our ancestors imagined. And yet, also more comprehensible. We can write equations, make predictions, test ideas against observation. Despite all our theories and equations, despite mathematical sophistication and observational precision, wonder remains. The sheer fact that anything exists, that we exist to ask about it, that the universe gave rise to consciousness contemplating its own origins. This is profound. We are stardust, quite literally. The atoms in your body were forged in the cores of dying stars, scattered into space, incorporated into a new solar system, assembled into a living being. You are the universe experiencing itself, a local eddy in the cosmic flow. That this universe, or multiverse, exists before, after, or timelessly alongside our Big Bang doesn't diminish the wonder. If anything, it amplifies it. Reality is vaster than we thought. More universes, more possibilities, more structure, more mystery. And we, improbable conscious observers on a small planet orbiting an ordinary star, can grasp fragments of this vastness. We can write equations describing the first seconds of our universe. We can propose models of what came before time. We can probe the nature of reality itself. This is the great gift of consciousness, the ability to wonder, to question, to seek understanding. Other animals live in the eternal present. They experience but do not question. They are but do not ask why they are. We alone, as far as we know, look up at the night sky and ask, where did all this come from? What existed before the beginning? Why is there something rather than nothing? These questions may not have final answers, but asking them makes us human. Perhaps the deepest lesson from exploring what existed before the Big Bang is learning to live with uncertainty. We may never know the final answer. Science progresses, but complete knowledge may be forever beyond reach. This is difficult for humans. We crave certainty, closure, definitive answers. We want to know not just how things work, but why they are, what the ultimate explanation is, where the chain of causation ends. But reality may not provide such closure. The universe is not obligated to be fully comprehensible to human minds. We evolved to hunt, gather, navigate social groups, survive on an African savanna. That our brains can grasp quantum mechanics and general relativity at all is remarkable. That they might fail to grasp the ultimate nature of reality is unsurprising. Yet we've come astonishingly far. From wondering if the sun was a god to understanding nuclear fusion and stellar cores. From thinking the Milky Way was the entire universe to discovering hundreds of billions of galaxies. From imagining the universe eternal and unchanging to discovering the Big Bang and cosmic expansion. Each generation pushes the boundary of knowledge further. Questions that seemed unanswerable become answerable. Mysteries that seemed permanent yield to new mathematics, new observations, new conceptual frameworks. The question of what existed before the Big Bang stands at this boundary now. We have theories, models, mathematics. We have observations that constrain possibilities, but we don't yet have certainty, and we may never have it. Learning to be comfortable with this uncertainty while continuing to push against it is the mark of intellectual maturity. As we near the end of this journey, it's worth reflecting on what these cosmic questions mean for human life. Does it matter to our daily existence what existed before the Big Bang? Does it change how we should live? In practical terms, perhaps not. Whether the universe began from a quantum fluctuation or a bouncing cycle doesn't affect whether you should be kind to others, pursue meaningful work, cherish relationships. The ethical dimensions of life remain regardless of cosmological origins. But in another sense, it matters profoundly. How we understand our place in reality shapes how we understand ourselves. If we're cosmic accidents in a single universe that popped randomly into existence, that suggests one perspective. If we're inevitable consequences of eternal physical laws, that suggests another. If we're in one bubble among infinitely many, each with different laws, then our particular universe and its properties are contingent, arbitrary. If we're in a cyclic universe that has existed forever, then we're part of an eternal pattern. If we're in a mathematical structure that exists timelessly, then our existence is necessary in a Platonic sense. These different cosmological pictures offer different frameworks for meaning. They don't determine meaning. Humans create meaning through choices, and values, but they provide different contexts. Perhaps the most important insight is simply this: we are part of something vast, ancient, mysterious. We emerged from cosmic processes billions of years in the making. We are temporary patterns in an eternal flow, brief candles in an infinite darkness, conscious observers in an unconscious universe. This should inspire both humility and wonder. Humility at our cosmic insignificance, wonder at our cosmic improbability.